What's up guys, my name is Rustagi and today I'm going to be teaching you everything you need to know for AP Calculus AB and BC Unit 5. And please stay tuned all the way till the end to learn all the topics and practice with some free response questions with detailed solutions. Now if you haven't already, please go to the description right now and get my free AP Calculus AB and BC books because those books have everything you need to know to get a 5 and an A in your class. So what are you waiting for? Get it right now, and now let's begin immediately with Unit 5. Now Unit 5 starts with the mean value theorem. Now the mean value theorem says that if we have a function f that is continuous for the closed interval from a to b and it's differentiable for the open interval from a to b, then there exists a point c in the interval from a to b, in the closed interval from a to b, such that f prime of c equals to f of b minus f of a divided by b minus a. And this basically means that the secant line that connects the point from A to B, the slope of that, there will be another point between the points A and B such that the slopes of both the secant line and the tangent line, they're both equal. Now let's look at an example of the mean value theorem. Now this curve in front of you represents 2x minus x squared. So y equals to 2x minus x squared. And now I'm going to be working with the points from x equals to 1 to x equals to 3. So now the red line you see, that represents a tangent line, and then the yellow line represents the secant line. So by the mean value theorem we know that there exists a red line, right, which is the tangent line, such that the slope of that equals to the slope of the secant line. So now let's verify this. So that means f prime of c equals to f of 3 minus f of 1 divided by 3 minus 1. And since f of x equals to 2x minus x squared, we can plug in x equals to 3 and x equals to 1 into this expression to find the slope of the secant line. And after we do that, we can find that f prime of c equals to negative 2. Now let's verify and find the value c such that f prime of c equals to minus 2. So we know that f of x equals to 2x minus x squared. So we can find the first derivative of this by using the power rule. And we can find that the derivative is 2 minus 2x. And this means that f prime of c is 2 minus 2c. And that equals to negative 2. And then we can solve that for c to find that c equals to 2. Now let's go over the intermediate value theorem. Now the intermediate value theorem also has some conditions. Basically the function f must be continuous for the closed interval from a to b. And in that case, there will be a number n in the open interval from f of a to f of b between the two endpoints basically, such that c exists in the open interval from a to b, so that f of c equals to n. Now this is used to verify if a specific number exists within an interval. Now let's look at an example. Now this curve that you see, I have connected the points 0, negative 1 to 3, 2. So basically the y values of the two endpoints are negative 1 and 2. And this means that if this function is continuous, now by the intermediate value theorem, this function will always have a value between negative 1 and 2 because those are the two endpoints. Now the extreme value theorem is extremely important, and it's basically used when our function f is continuous for the closed interval from a to b. And if that is satisfied, then this interval will have the highest and lowest value in that interval. And that brings us to global and relative extrema. Now to find relative extrema, first note the difference between relative extrema and global extrema. There can be multiple local extremas. For example, there can be 2 or 3 local maximums and maybe 2 or 3 local minimums. However, there can only be exactly one global maximum and exactly one global minimum for an interval. So to find all the relative extrema and even absolute extrema and global extrema mean the same thing, by the way. But to do this, we must know critical points. So a critical point exists at points for which the first derivative is either 0 or undefined. And remember that all local extrema must occur at critical points. So to find the local extrema, you find all critical points. However, it does not mean that a local extrema must exist at all critical points. That is not true. Now, is a function increasing or decreasing? Well, a function is increasing when the first derivative is greater than 0. And it's decreasing when the first derivative is less than 0. So, to find the intervals for when a function is increasing or decreasing, you first find all critical points. Then you mark a number line. You make a number line to mark each critical point. And then you plug in a value in between each critical point, and you substitute it And then you substitute that into your expression for the first derivative. And if your value is positive, then it means the function increases between those two critical points. And if it's negative, then that means the function decreases between those two critical points. So let's look at an example. Let's find the intervals when x squared plus x plus 4 divided by x plus 1 is increasing or decreasing. Well, we first find the first derivative, so we can find the critical points using that. So we use the quotient rule to find that the derivative is x squared plus 2x minus 3 over x plus 1 squared. Now we can factor this to get x minus 1 times x plus 3 divided by x plus 1 squared. And now critical points will exist at 1, minus 3, and negative 1. So we plot all of those critical points out. Now we plug in a value between each critical points. And don't forget that we must also plug in a value to the left of the leftmost critical point and a value to the right of the rightmost critical point. So we plug in a value to the left of negative 3. So we'll plug in negative 4. And if we plug that in, we get a positive number. Now we plug in a value between negative 3 and negative 1. So let's plug in negative 2. And if we plug in negative 2, we get that the first derivative is negative. Now let's plug in a value between negative 1 and 1. So let's plug in 0. And then we get a negative number. Now let's plug in a value above 1, so greater than 1. So if we plug in 2, we get a positive number. And this means that the function increases to the left of negative 3 and to the right of 1, but it's decreasing from negative 3 to negative 1 and from negative 1 to 1. Now the first derivative test allows us to find the relative extrema. You must still find all critical points, but now you will be working with the first derivative sign changes. So when it changes from negative to positive at a critical point, then we have a relative minimum. However, if it changes from positive to negative, then we have a relative maximum. And again, use the number line method to keep track of positive and negative signs. So basically, the first derivative test allows us to find relative extrema. Now the candidates test is what allows us to find absolute extrema. So again, you will still find the critical points. However, now you don't care about sign changes much. Instead, you can directly find the function's value for each critical point and the endpoints. You must test the endpoints of the interval because a global maximum or global minimum can occur at the endpoints. So don't forget to check that. Now, determining concavity. So concave up function means that the second derivative is greater than 0 and concave down means that the second derivative is less than 0. Now to find the intervals of concavity, you set the expression for the second derivative to 0. And then you solve for x and then you use the number line method again to figure out when it's concave up or concave down. And then an inflection point occurs when the sign of the second derivative changes at a certain point. Now the second derivative test. So the first derivative test allows us to find the relative extrema. Now the second derivative test also lets us do that, but it's a little different. So first you will find all points C for which f prime of c equals to 0. Now if f prime of c equals to 0, and f double prime of c is greater than 0, then we will have a relative minimum. And if f prime of c equals to 0 and f double prime of c is less than 0, then we will have a relative maximum. Now let's connect the function to the first and second derivative. Well, I'm going to give you an example. Well, an object's speed will be increasing if the acceleration and velocity have the same sign, but the speed will be decreasing if acceleration and velocity have different signs. Now in general, when is a function increasing and when is it decreasing? Well, it's increasing when the first derivative is positive and it's decreasing when the first derivative is negative. Now, when is the function's rate of change increasing or decreasing? Well, a function's rate of change is increasing when the second derivative is greater than 0 and the rate of change is decreasing when the second derivative is less than 0. Now, optimization is basically where all the topics that we've learned so far from this unit, this is where it's going to be applied. So basically for optimization problems, you'll be given a word problem and then you will want to write an equation to represent the problem. And you use variables to represent the unknowns. And then you draw diagrams whenever you can. And don't forget all that you've learned about critical points and all the tests. Now let's look at an example. Two numbers sum up to 32. What is the least value of the sum of the squares? Well, let's say our two numbers are x and y. And that means x plus y equals to 32. And then the sum of the squares is x squared plus y squared. And we don't know what this is. Now, we don't want to deal with so many variables at once, so we can use the first equation, x plus y equals to 32, and then we can subtract both sides by x to get an expression for y, and that means y equals to 32 minus x. So we substitute that in, and now we know that we want to find the least value for x squared plus 32 minus x squared. So we can expand this to get 2x squared minus 64x plus 1024. Now we can find the first derivative of this to get 4x minus 64. And this equals to 0 when x equals to 16. So a critical point exists at x equals to 16. And that means the answer is 16. Both numbers must be 16 because the critical point occurs at 16. We can also see this by if we plug in a value less than 16, such as 15, into the first derivative, which is 4x minus 64, we get a negative number. But if we plug in a value greater than 16, such as 17, we get a positive number. So the sign changes from minus to positive, and that means we have a minimum at that point. So 16 is indeed the answer. Now let's look at another example. We have a function y equals to the square root of x. Now we want to find the distance of the point closest to 3, 0 on this function. So a point on this function can be represented as x, square root of x. And then we can write an expression for the distance between the 2 points as the square root of x minus 3 squared plus the square root of x squared. And we can expand this to get the square root of x squared minus 5x plus 9. And now we can differentiate the inside expression inside the square root, which is x squared minus 5x plus 9. And finding the first derivative of that gives us 2x minus 5. And then we can set this equal to 0 to find the critical points, which means that there's a critical point at 5 over 2. So now we know that x equals to 5 over 2. So we can plug that into our expression for the distance to find the minimum distance between a point on the function and the given point. So we plug in 5 over 2 into our expression for distance to find that the least distance is the square root of 11 over 4. Now, exploring behaviors of implicit relations. Now, there's nothing new to learn in this topic. It's just that if you're differentiating and you have to use implicit differentiation to find the derivative, then critical points still exist with the same rules that we learned before, such as critical points exist when the first derivative is 0 or undefined. Now, this means that even if the method of differentiating is different, everything else remains the same. For example, the first derivative test, the second derivative test can still be used. Now let's look at a free response question from an actual AP exam. Now please pause the video to try the problem. This is a very important problem. Now by now I hope that you actually pause the video to try the problem. So part A wants us to find if the function f has a relative minimum, a relative maximum, or neither at x equals to 6. Well, a relative extrema will exist if the sign changes at x equals to 6. So in this problem, we're already given the graph for the first derivative. So we can see that at the points to the left of 6, it's above the x-axis, so it's greater than 0. And then the first derivative is still greater than 0 to the right of 6. So the sign does not change, which means that neither a relative minimum nor a relative maximum exists at x equals to 6. Now part B says, on what open intervals, if any, is the graph of f concave down? Well, a function will be concave down when the second derivative is negative, which means that the first derivative is decreasing. So we can investigate this graph, right? And we can see that the first derivative is decreasing from x equals to minus 2 to 0 and x equals to 4 to 6. Now in part C, we want to evaluate this limit. Now if we directly substitute 2 for the expression given in part C, we get an indeterminate form of 0 over 0. So now we apply L'Hopital's rule. So we can differentiate 6 times f of x minus 3 of x, which is the numerator. So we can first differentiate the numerator to get 6 times f prime of x minus 3, and then we differentiate the denominator to get 2x minus 5. And now if we directly substitute in 2, we get 6 times f prime of 2, and we can use our graph to find that f prime of 2 is 0, minus 3 over 2 times 2 minus 5. And we can simplify this to get 3 for the answer. Now thank you so much for watching this video. And please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams, such as the AP exams. And also, don't forget to follow the Instagram, if you have Instagram, to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.